Hi, welcome back. Today I'm going to talk about formal verification using Dafny. In the previous segment, we talked about some small problems. I will just continue with that discussion and wrap it up today. So the problem is very interesting, actually. The goal is to add two numbers, x and y, with some properties. Small program, but still interesting to verify formally. The condition the program should satisfy is that it has to take x and multiply it by 2. So 2 times x plus y should be the behavior we want the program to satisfy. Very simple, right? However, we want to make the program complicated. Maybe you're writing an obfuscated program. Okay, we don't want to disclose 2 times x plus y. You want to make the reverse engineering somewhat challenging, if you want to call that way. So the program is actually written using a while loop here, which is supposed to achieve this goal of multiplying 2 times x plus y. Okay, but if you just formally verify it right now, let's run it and see what happens. It says the ensures condition is not satisfying, right? You see a little wiggly here, right? Let me show you that more precisely. So there's a little wiggly symbol. That means there is a problem that we are not able to satisfy, and we are having 2 error messages coming from formal verification tool Dafny. So let's try to fix this. So what is the first thing we need to fix? If you read this carefully, this program appears to be doing just x plus y, right? The reason I say so is this: our n is assigned to y, and of course our r is x here. So while n is not equal to 0, we keep decreasing n. So that means we add from r equal to x all the way to y steps. That means it should be returning x plus y. So let's see whether that's true or not for a moment. But that's not the goal. The goal is to do 2 times x plus y. So let's try this. Okay. So as I guessed, the program verification went successful. There's no mistake in the sense that the outcome of this program matches the expected behavior that is formalized here, right? Ensures behavior is correct. Okay. However, remember, the goal is to do 2 times x plus y. So now this is something simple to fix. What if I just put 2 here? Invariant is 2 times x plus y, right? Minus n. The reason is, let's start at the beginning. At the beginning, n is y, right? So what will happen to this expression? This becomes 0, and r is 2 times x, which is perfectly fine. No, not yet. R is x here, so x is not equal to 2 times x. So let's run it and see what happens. It should still fail. Yeah, it still fails. So as I said, our r is wrong, initialized to a wrong number. So we should do say 2 times. Let's try this. Yep, it verified correctly. And now we have successfully proved that this program, when it terminates, will indeed return 2 times x plus y. Okay, I'm not sure whether this works. Let me try. It should be also working, right? Oh, you know, this language doesn't allow this kind of operation because it declared x and y to be int type. It's not exactly like the regular C int. That's the reason they don't like the shift operators, because it uses SMT solvers under the hood. So I will stick to what they have given us. Okay, so anyway, so this is verified now. No mistake. Let's introduce some bugs in the code, right? Let's say sometimes people make mistakes in small code. I have made lots of mistakes like that. So what if I just put instead of n minus 1, I put r minus 1. Okay, hopefully mistake is detected by the verifier. Yeah, that's nice. The could not prove loop termination of the loop. First warning. Second warning is that the loop invariant might not be maintained by the loop. So that's very good. So it was able to detect this. Sometimes when the program is using loops, you need to show what is being decreased so that the verification condition can be established properly. Okay, so let me revert this bug, right? Let me just change it to n minus 1, and we should formally verify this again. And verify successfully, 0 errors. Let me make some more mistakes. It's fun to make mistakes and see whether the verifier detects it. Okay, so what if I just go back here, and for some reason this is dancing up a little bit. I'm going to make a small mistake, one more mistake. What if I put r equal to r plus 2? Yeah, invariant violation, loop invariant violated. Okay, this is really good. It was able to verify correctness of code. Of course, you need to formally specify the loop invariant. What is the behavior we expect the loop to achieve in every time the loop runs, as we talked about earlier. So I will just change this to 1. and now we should be able to go. Okay, so it's verified successfully, 0 errors. What if my loop invariant is a little wacky and I made a small mistake? Let's say I replace this by n. Okay, so what happened? It's still, yep, you see a loop invariant is failing, and the tool was able to detect that there's mismatch. So my loop invariant was wrong, so I can fix that now, and I don't have to run it again. So we checked it. Okay, well, let me make one more mistake. Since we are making mistakes, it's good to make more. What if I just do r equal to r plus n? Yep. Oh, I have to put syntax. This is not regular like C programming or something like that. I have to follow their syntax. Okay. Hopefully this is also detected as a problem. Yep. It's again a problem. So this is nice that as soon as you are able to specify what is the behavior you expect the program, you can formally verify using this neat idea. Okay. All right. That's basically it. Thank you very much.